introduction to organic chemistry, chemical behavior is typically treated as a direct function of electronegativity. We are taught that the more electronegative an atom is, the stronger its pull on electrons, and consequently, the more acidic the proton attached to it will be. This chart compares methane to hydrogen fluoride. Carbon has an electronegativity of 2.5, and methane has a pKa of around 50, meaning it rarely acts as an acid. Fluorine, the most electronegative element on the periodic table at 4.0, yields a pKa of 3.2. So far, the rule holds. But if we move straight down the periodic table to iodine, the logic breaks. Iodine has an electronegativity of 2.5, identical to carbon, yet hydrogen iodide has a pKa of -10. It is an acid roughly 10 million times stronger than hydrogen fluoride, despite being formed from a significantly less electronegative element. Electronegativity alone cannot account for these observed pKa values. The conventional, proton-centric view of acidity fails to reflect the underlying structural mechanics of the molecule. Acidity measures the thermodynamic survival of the electrons that remain after a proton departs. When an acid loses a proton, it becomes what is known as a conjugate base. This conjugate base is the true protagonist of any acid-base reaction. If the remaining molecular structure can efficiently stabilize the newly acquired negative formal charge, the system sits at a lower overall energy state. Therefore, it will readily shed the proton. If the molecule cannot stabilize that resulting charge, it holds on to the proton tightly, avoiding the transition into a high energy state. This behavior is governed by the probabilities and wave functions that form the core of quantum mechanics. Erwin Schrödinger's equations dictate that closely confined electrons possess higher kinetic energy, driving physical instability. To accurately predict chemical acidity, we must evaluate 4 distinct structural factors that dictate a molecule's ability to disperse and stabilize its electron density. The first factor is the physical geometry of the specific atom bearing the charge. Across a single row of the periodic table, from carbon to fluorine, atomic volume remains relatively constant. Along this horizontal axis, electronegativity successfully predicts conjugate base stability. Moving vertically down a column, that rule collapses because the physical size of the atoms expands. This diagram compares the spatial footprint of a fluoride ion at 133 picometers against an iodide ion at 220. When hydrogen fluoride loses a proton, the full negative charge is forced into fluoride's tiny volume, creating electrostatic repulsion. Iodide's massive volume allows the same charge to diffuse over a larger area, dropping charge density and decreasing energy. When evaluating elements vertically down a group, the ability to physically diffuse charge over a larger atomic volume dictates stability, overriding pure electronegativity. The second stabilization factor is the mesomeric effect, routinely referred to as resonance. Empirical data provides proof. Phenol, an aromatic ring with a hydroxyl group, is approximately 1 million times more acidic than water. The reason is structural. Look at the methoxide ion, the conjugate base of methanol. The negative formal charge is permanently isolated on a single oxygen atom. In the phenoxide ion, the oxygen's p orbital sits precisely parallel to the adjacent benzene ring's pi system. This alignment triggers an electron cascade. The charge flows out of the oxygen, delocalizing across the ortho and para carbons of the ring. Geometrically spreading a formal charge across multiple distinct atoms results in an immediate lowering of the system's overall energy. The third factor is the inductive effect. Unlike resonance, this mechanism operates through standard sigma bonds, so it does not require an overlapping pi system to function. Consider standard acetic acid alongside fluoroacetic acid. A single fluorine substitution increases the acidity of the molecule by orders of magnitude. This occurs because highly electronegative atoms act at a distance, dragging electron density through the structural framework of the molecule. In fluoroacetic acid, the fluorine atom pulls the surrounding electron density toward itself, altering the entire carbon skeleton's distribution. This continuous withdrawal drains electron density away from the carboxylate oxygen. It acts as an internal relief valve, stabilizing the conjugate base. This effect places structural tension on the molecule, actively distributing the energetic load outward from the reaction site. Inductive effects demonstrate that chemical stability is a global property of the entire molecule, rather than a localized trait of the charged atom. The final factor is orbital hybridization, specifically the concept known as S-character. This data table tracks carbon bond acidity. Ethane's pKa is 50, ethylene drops to 44, acetylene leaps to 25. The distinction is the S-character ratio. An sp orbital has 50% S-character, while an sp3 contains only 25%. Spherical s orbitals hold the alkyne's lone pair physically close to the positively charged nucleus for stabilization. In an sp3 hybridized alkane, the elongated orbital pushes electrons further from the nucleus's stabilizing positive charge. Higher S-character guarantees tighter electrostatic proximity to the nucleus. This proximity provides stabilization, making alkynes uniquely acidic among hydrocarbons. Predicting real-world chemical behavior requires analyzing molecules where these stabilization forces operate simultaneously, often pulling the structure in opposite directions. We can observe this competition by ranking the acidity of pure phenol against two derivatives, p-cresol and p-nitrophenol. In p-nitrophenol, the nitro group acts as an electron vacuum. It applies a negative mesomeric effect through resonance and a negative inductive effect through the sigma bonds. This dual withdrawal pulls the negative charge out of the phenoxide oxygen and into the nitro group. It stabilizes the anion, making it the strongest acid of the three. In p-cresol, the attached methyl group exerts the opposite force. Through a positive inductive effect and hyperconjugation, it pumps electron density back into the benzene ring. This influx of electrons actively works against the oxygen, crowding it with density and destabilizing the anion. This makes p-cresol a weaker acid than pure phenol. Substituent groups act as a mathematical tug-of-war over electron density. The victor dictates the molecule's ultimate survival. Organic chemistry operates on the resilience of the electrons left behind. Whether a chemical reaction involves acids, bases, carbanions, or reactive intermediates, the mechanics of charge distribution remain perfectly consistent. The molecule that most efficiently disperses its electron density is the molecule that survives.